In this video, we're going to say a bit about the bending equation. We're also going to do example 1 from page 40 of the course notes. The bending equation is given in this form here. We've got m over I is equal to, this funny shape is called sigma, it's a lowercase Greek letter, divided by y. And I'll introduce what these terms are and what their units are before we get into the example. So M we've encountered already in learning outcome 1. This is the applied bending moment at the section, usually referred to the maximum bending moment at the section. And in the example we're about to do, you see why that's particularly relevant. I is the second moment of area about the neutral axis in this case being the centroid. And we've been dealing with this already. Sigma is the bending stress at any distance y from the neutral axis, and y is that distance from the neutral axis. So let's talk about what these things are. Stress is the force per unit area that's being applied, that's the load that's been applied to our beam, and y, the distance from the neutral axis, that means the distance from the centroid to the point at which the force is applied. So that means that our type of questions is going to be from the centroid to the end of the section, usually the top of the section, if we're looking at it with the force being applied from above. The units are all given here. Our units for length are millimeters and our units for force are newtons. So it means that sigma is going to be newtons per millimeter squared because it's force per unit area. We already have encountered bending moment before, and specifically we're going to use Newton millimeters, that's force times length unit. And y is going to be a distance in millimeters, and like the distances we've encountered so far, they're in millimeters, and we've already been working with I in millimeters to the power of 4. And the course note gives us a different version of the formula, and the reason for that is just for quickness. Although we can rearrange the formula ourselves to get any one of these quantities, quite often we'll be working out the bending stress in a particular example, and this saves us doing a bit of rearranging. So let's look at the first example from the course notes, having introduced this new concept to us. So we're given an example of a steel beam, an I-beam, which we again encounter often. Give them a wee bit of story here. It's using an offshore platform. It's to be loaded with a uniformly distributed load of 7 kilonewtons per meter, as shown below. And neglecting the self-weight of the beam, and we will always neglect the self-weight of the beam in these questions. It wants us to calculate the maximum bending stress in the beam. Let's pause and have a think about what we're actually doing here. So the thing that we want to find is sigma. That's the maximum bending stress. That's the rearranged version of our formula. So we've been asked to find sigma, and sigma is equal to m, that's our maximum bending moment, because maximum stress times y divided by I. Now, we can calculate I. We've been calculating I already. We'll get to that in a second. And y is going to be something relatively straightforward. We can calculate y straight away. If our force is being applied here, y is the difference between where the force is applied and our centroid. So that's half of 300. So we can just write straight away y is equal to 150 millimeters. That's how we find y in a question like this. We write it out like so. We can also find m quickly as well. We know how to calculate bending moment in a section of beam. We could go about what we've done in learning outcome 1, but we could also observe the type of beam we've been presented with here. The support on the top of this beam is the same as one of our standard cases from learning outcome 1, a simply supported beam with a single UDL only along the length of the beam, and that's what we have here. We've got a UDL along the top, and we've got a simple support at either end. So that's just like this example here. And when we have this, it tells us that the maximum bending moment is given by this relationship here, WL squared divided by 8. So W is our UDL, and L, length of the beam, is 10 meters, and well, we divide that by 8, but we have to be careful here, because remember the units we're aiming for are kilonewtons, are Newton millimeters, not kilonewton meters. But we'll take this a step at a time and see what it takes us. So first of all, we can work out our value for m. M is going to be equal to W, which is 7, and we can leave it in kilonewton meters just now because we're working in meters, times the length of the beam, 10, which is squared, divided by 8. So we have 7 times 10 divided by 8, which is 700 divided by 8, and we'll see what that is. That's 87.5, but be careful again, it's 87.5 kilonewton meters. So what's this going to be in Newton millimeters? Well, if we remember that a kilonewton is 1,000 newtons, and a millimeter, and a meter is 1,000 millimeters, that means it's actually going to be 87.5 times 1,000, because 1,000 newtons a kilonewton, times 1,000, because 1,000 millimeters in a meter. So we can actually just write this simply as 87.5 times 10 to the 6. So that just means add 6 zeros afterwards, and that's what multiplying by 1,000 twice does. Times 10 to 6 Newton millimeters. And so we've got our units in the form we require. Now let's get rid of this standard case just now. We don't need that. So we've got our value for m. And in a type of question like this, when you're given a UDL value like this, always be looking out for a standard case, because although we could ask you to go back and break it down and work out the maximum bending moment, we've covered this in Learning Outcome 1 already. We don't need to go back if there's going to be a straightforward way to obtain this. So we now have y and m. All that remains is for us to find I, and we only have to calculate the second moment of area about the x axis here. So this is where I'm going to diverge from the course notes, because the course notes uses an alternative method from the parallel axis principle, and the method is not incorrect, but it is the method most associated with people failing Learning Outcome 2, and the reason is this: it's simpler, which means there's less opportunities for you to demonstrate how you got the answer. It isn't wrong, and if you use it and do it correctly, you can pass a TMA question, but if you get it wrong, it's much harder for you to be awarded any marks at all for the question. So that's why I'm going to solve this problem differently using the parallel axis principle. I've already done an example video on this, so I won't go into as much detail, but I will still include all the important steps, including splitting up our I-beam into 3 areas, 1, 2, and 3, recognizing that areas 1 and 2, areas 1 and 3, I should say, have the same second moment of area, but the x-axis. For each of those, they have a depth of 15 millimeters, a breadth of 100 millimeters, an area of 15 times 100, which is 1,500 millimeters, and the distance c is going to be from the centroid to halfway up the depth of the flange. And so the flange has got a depth of 15, that means 7.5. So it means that the value for C is going to be 150 minus 7.5. I'll draw that quickly in the diagram here. There's a distance from here to here, from the centroid to the top of the beam, which is effectively our y distance is 150. This distance I'm marking purple halfway down is 7.5, because 7.5 is half of 15. So that means we have a value for C of 142.5 millimeters. This allows us to calculate our second moment of area for rectangles 1 and 3. So Ixx is equal to BD cubed over 12 plus AC squared And that gives us an answer here of 30487,500 millimeters to the power 4. And so that's the answer for rectangles 1 and 3. For rectangle 2, then we're just dealing with a thin rectangle of this order. Looking back at our diagram, we can see it has a width 10 and its depth, the height of it, has to be equal to 300 minus the height of the two flanges. So 300 minus 15 minus 15, which is 300 minus 30. So it says 270 as the height of the, or depth, I should say, of the area 2. And we just find this using our standard formula for a rectangle because it has the same XX centroid as the I-beam as a whole. So BD cubed divided by 12 is equal to 10 times 270 cubed divided by 12. Put that into our calculator. We can get the second moment of area for our final area. And that gives us a value of 1640250 millimeters to the power 4. Now to find the second moment of area about the XX axis for the I-beam, we add these three areas together. So we have 2 times the value we got for the first rectangle, because that's the same as for the third. So that's for 1 and 3. They're both this number here, 30487,500. And to that we add the value for area 2, which we've just worked out. And this gives us a value of 773,77500. And we'll put this in the notation. We get the same answer as the method in the course notes of 77.377 times 10 to the 6. Now, of course, strictly speaking, that should be 378 if we're rounding, but let's keep the numbers the same as the example so we don't diverge from them too much. So we've got our value for y, or y max, because it's going to be the maximum distance at the top of the beam. We've got a value for m, and we've got a value for I. So we now have everything we need to calculate the answer here. So we'll go across to where we wrote our formula and put in these numbers. So sigma is equal to m. We got m by the value of the UDL, and recognize we had a standard case. So we just put in our values for m and for the length of the beam to get the sort of value for the UDL, which was W, and our value for L, the length of the beam. And it gave us a value for m, which we converted into Newton millimeters of 87.5 times 10 to the 6. Our value for y, actually still marked on the diagram here, is this 150. It's the distance between the centroid and the top of the flange, or alternatively the centroid and the bottom of the bottom flange. So we have multiplied by 150 here. And then the whole thing is divided by our second moment of area about the axis we're considering, which is the XX axis. And that's 77.377 times 10 to the 6 millimeters to the power 4. And putting all of this into our formula, using the correct units, and then calculating in our calculator, we're going to have 169.6 Newton millimeter squared. And I think if we go back and look, we see it's actually newtons per millimeter squared. Another little mistake in the course, so newtons per millimeter squared. And that's the statement that we would write out, and I'll save myself writing it and just copy it from the notes, would say the maximum bending stress in the beam is 169.6 newtons per millimeter squared. And it's important we say maximum bending stress because we're basing this on maximum bending moment. This is not going to be the bending stress at every point along the beam that we're considering, but the maximum I think is going to be important because that's going to be the criteria by which a beam is deformed or fails at. And that's the first example of this from the course notes, with the alternative that we use, the parallel axis principle, which is the correct way to calculate the second moment of area for an I-beam.